Okay, now I'm recording. So let me just real quick say that one more time so that it is on the recording. This will mostly be a module preview. So whatever module is upcoming, that will be what we'll be previewing this week. We will be doing the end of module 1 and all of module 2. But at the beginning of any one of these, if anybody has any questions about anything in the class, any of the content we're going over, I'll usually start out with asking any questions. Okay, so we are going to start with talking about liquid properties. So, as I was saying, in class, we have at the end of 1211, we talked about gases, and now we're kind of in our liquids. And then our next module will be about solids. So in this one, we really care about our liquid properties, and we have a couple of ones that are important, and they're all going to be based on intermolecular forces themselves. So our first one is going to be viscosity, which is a resistance to flow. Or a liquid's resistance to flowing. So we usually have things that are viscous or watery. So those are our kind of two options. So watery, we know, very thin liquid, if we're kind of describing it in like a term. So it is going to be something that can flow very easily. And this is because the particles don't stick together. And then something that is viscous is something that's kind of a thick liquid that flows it has a lot of resistance to that flow. That's gonna be stuff like motor oil or honey. So intermolecular forces do play a big role in viscosity, but it's more how tangled things can get. So I like to think about things that are watery are going to be small molecules that can easily pass by each other, whether or not they have strong intermolecular forces or not. Like water has, as far as a small molecule goes, it has pretty strong intermolecular forces. However, it's not very viscous. When we think about a viscous liquid, it's one where our molecules kind of get tangled within each other. So viscous species are going to be things that are linear and can easily tangle. So things without very many branches. And then after that, we start to look at intermolecular forces. So honey, for instance, is a long molecule, but it has a lot of OH or OH groups in it. So it has a lot of hydrogen bonding. So it has hydrogen bonding in addition to being a kind of linear structure. And then it's a bunch of sugar molecules in a linear structure. And then things like motor oils, the really thick ones, are really long hydrocarbons. So viscous fluids tend to be things that are generally, like I said, longer and have more ability to tangle. Kind of think about like spaghetti noodles. So let me see if I can get. Try to find a specific picture, but I'm not able to find it, so I'm not going to worry too much about it. But yeah. Oh wait. Yeah. But yeah, just the longer, larger molar mass, generally the more viscous. Okay. Next thing is surface tension. Surface tension is essentially the amount of energy that is needed to break the amount of energy required to increase the surface area of a liquid. And this is going to be based entirely on intermolecular forces. So our IMFs are intermolecular forces. Water is a substance that has a very high surface tension. We can kind of think about it as kind of the ability to kind of break through the surface. And we can see it kind of applied in real life when we think about like bugs and leaves and stuff like that that are able to float on the surface without breaking through the surface because of the high surface tension that water has. Something like mercury has an even higher surface tension. Mercury is our only liquid metal and only one of two liquid elements. And I don't know if anybody's ever played with liquid mercury. You probably haven't. It's probably for the best. But you really have to kind of, if you try and like poke it, and again, you shouldn't do this with your finger, but like if you have gloves on, it's really hard to kind of like permeate that surface. It kind of just kind of spreads out a little bit and doesn't really pierce because of the high surface tension. So with surface tension, what we're looking at is the intermolecular force, the difference in intermolecular forces between the bulk liquid and what's above the liquid. So kind of the way we think about this. Can't find any of the images that I want today. Here we go. That's what I want. So with surface tension, we're thinking about how kind of the water interacts with its. Oh, let me do it different. That image is really hard to see. Sorry about that. There we go. If we think about the surface of water, we've got water molecules on the surface, and water is polar. And then air, which is above our water, is non-polar. So the water is not attracted to the air because water is polar and air is non-polar. So it's going to have an overall force, the intermolecular forces pulling that water molecule down. In the bulk of the water, we've got the intermolecular forces pulling in all different directions. But because on the surface that pull is downwards, it is going to kind of like tighten the surface and make it so we can put as few water molecules on the surface as possible. And that is the reason for surface tension, is because of that overall downward pull on those water molecules, and kind of the decrease, the water itself trying to decrease interaction with that non-polar air. This is responsible again for like bugs being able to walk across the surface of water, as well as things like water droplets being spherical in nature instead of being kind of spread out. It kind of wants to interact with just other water molecules and minimize the amount of contact it has with the non-polar air. Okay, our next liquid property we're going to look at is capillary action. And capillary action is the property that's responsible for a liquid going up a capillary, which is a thin tube. So capillary action, we have kind of two properties of liquids occurring at the same time. We have adhesive forces and cohesive forces. So adhesive forces this is where something wants to adhere to something else or is attracted to something else. So this is attraction of a substance to a surface. And this is what we see when we think about water going up the sides of a glass tube and producing a meniscus. So if we've got a glass tube and that water goes up that glass tube, it's because that water is adhering to the sides of that tube. And this right here, you guys probably already familiar with this, hopefully, is a meniscus. And let's see if I can spell meniscus. Meniscus? I don't think that's how you spell it. So the meniscus is kind of that curve that we get. You have definitely seen this in lab when you're trying to read some sort of container or like a graduated cylinder or a beaker. You can see that you always read to the bottom of the meniscus. So that is our adhesive forces. And then we also have cohesive forces. And this is the attraction of a substance to itself. So just like we saw with surface tension, where the water molecules are attracted to each other, so they try and minimize interaction with things that aren't itself. That's what we're looking at here for those cohesive forces. So both of these are going to cause a liquid to go up a capillary, as long as that capillary is glass. And we're talking about polar. Well, if it's a glass capillary and a polar molecule, because glass itself is polar, or if we're looking at a non-polar substance going up a non-polar capillary. So essentially what kind of happens is the liquid is going to be attracted to the sides of the capillary and it's going to pull up. And then it's going to kind of like be attracted to itself and it's going to kind of pull in on itself. And it's going to keep going back and forth with that kind of, and it doesn't like actually go back and forth, but it's those two interactions that are occurring that cause that liquid to go up the capillary. And the thinner the capillary, the more that liquid will go up. But it's also going to be fighting against gravity as well. So thinner tube is going to lead to higher higher column of liquid. So we can see that with this image right here. I really like pictures, by the way. So this is capillary action. So we have a really big liquid and all we really see is that meniscus. But as we decrease the size of the capillary, we can see that the column gets smaller and smaller because we've got more adhesive forces that are going on and less effective gravity on the smaller tube or the smaller column of liquid. And just like with surface tension, which is based on intermolecular force, this too is based on intermolecular forces. So both of them, the stronger the intermolecular forces, the stronger the capillary action or the stronger the surface tension. Okay, so those are our various liquid properties. If you have any questions about any of them, just throw them in the chat and I would be happy to answer any questions you have. But if there are no questions, I'm going to move on to phase diagrams and phase changes. So I'll give you a second. Does anybody have any questions? Okay, so let's look at phase changes. So we already did a little bit of work on phase changes. So looking at the energy associated with those phase changes. So we looked at Q equals moles times by the delta H of our phase change, where this will be um, positive if we're talking about going from a solid to a liquid, or a liquid to a gas because we are increasing the amount of energy. Okay, that's fine. And then this will be negative if we're going the opposite direction. Gas to a liquid or liquid to a solid. And we've got a we have different phase diagrams that we look at that show what's going on at different temperatures and pressures. Do we actually we don't really talk about that in this chapter. No, we do. Okay. Our phase diagram looking at what's going on at various temperatures and pressures. So we can see that as we increase temperature, we can go from a solid to a liquid and a gas. And then our pressure also plays a role in this. So let's look a little bit at the points in a phase diagram. So we've got the triple point, which is right here. That triple point is going to be where all three states of matter are in equilibrium. And then we've got what's called the critical point, which is right here. And the critical point, anything above this point, is what's called a supercritical fluid. So our critical point is the last point where we have distinct liquid and gas phases. And as it's associated with a critical temperature and critical pressure. So anything above this, we are at a supercritical fluid. Where a supercritical fluid is a substance that has properties of, it has both gas and liquid properties. Supercritical fluid. Specifically, it's going to essentially have it's got a lower, it's got a viscosity similar to that of a gas, or a density similar to a gas, or I guess density between that of a gas and liquid. It has the ability to dissolve like liquid. Um, I'm trying to think of other properties. Um, do, 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 do. Oh, and it's generally miscible with gases. So, like I said, somewhere between those is where we get that supercritical fluid. So it has a much lower density than a liquid, but a little bit higher than that of a um, gas. However, we can, as that density increases, the solubility will also increase, or the ability to solubilize will increase. Okay. Then of course, in our phase diagram, we also have our three distinct phases. We have our solid, liquid, and gas phases. Our solid phase is going to be lowest temperature, highest pressure. Our gas is going to be our highest temperature, lowest pressure, and then our liquid will be in between those two. The other type of diagram we look at is called a heating or cooling curve. So that first, the one we just looked at a minute ago, the phase diagram, it looks at phases based on temperature and pressure. Here, we're going to be looking at phases as well, but we're looking at how much energy needs to be supplied to go from one phase to another. So with the heating and cooling curve, this is where we actually do calculations. If we are looking at temperature changes, then we use Q equals MC delta T, and then phase changes. Q equals moles times by delta H, generally, as delta H is almost always in kilojoules per mole. So this is what we were just talking a minute ago, and then I started talking about phase diagrams, so I stopped talking about it. But here, if we're looking at a heating curve, we look at the energy, sorry, the temperature. Temperature versus the energy added. So with a temperature or with a heating curve, we always start or generally start as a gas. And we increase as we increase the amount of energy added, we increase our heat. So this is a gas. And then we reach a plateau. This plateau is when we go from a gas state to a liquid state. Oh, I'm so sorry. I am all sorts of messing this up. This is starting at a solid. This is a solid. And this is going to go from our solid to our liquid. And then we continue adding in, once we have completely converted all of our solid into our liquid, we then will increase temperature further. And after that, we are increasing the temperature of the liquid itself until we reach another plateau, at which point we are converting from our liquid into our gas. And then you can heat up a gas as well. So some things to note, as we increase our energy, this is looking at both kind of an increase in kinetic energy and potential energy. As we are increasing temperature, we are increasing our kinetic energy. As we go from solid to liquid or liquid to gas, we are increasing our potential energy. Gas has the most potential energy, and most kinetic energy, and then solid will have the least. So each of these require energy, and the amount of energy is going to be based on what exactly we're doing. Going from one temperature to another, we're really just kind of making things move more quickly. But going from a solid to a liquid, we are what I like to think about it as like softening intermolecular forces. And then going from a liquid to gas, we are breaking intermolecular forces. So generally, this is going to require the most amount of energy because we have to entirely break intermolecular forces. Hopefully, you remember from 1211 that we consider gases to have no intermolecular forces. That's not entirely true, but for the most part, it is. So if we're going from a state that has intermolecular forces and can potentially have very strong intermolecular forces to a state where we have little to no intermolecular forces, we have to break those to go from one of those states to the other. So that's generally what's going on there. Okay. And then we get into our gas state at the end. Okay, we are not talking about liquid crystals, so that is everything for module 1. Let's get into module 2. I do have to leave at 6:45 today for another meeting. So I might have to do a second module 2 review, but I will definitely get through at least or preview at least the beginning part of module 2. So module 2, we are talking about solids. So when we're thinking about solids, this is when we have a lot of intermolecular forces or very strong intermolecular forces. And the type of substance we have, and the type of interaction between the particles within the solid will determine the type of solid that we form. So we have a couple of different types of solids. Well, we have our kind of generically, we can either have a well, I'll go for that in a minute. So our type of solids, we can have a metallic solid. And this is where we have metal. This is our bonded metal atoms. So these are metal atoms held together by metallic bonds. And we use what's called the electron C model to describe this. So our electron C model, we consider each of our metals to be just positive cations and all of the electrons to be dispersed all the way through the solid. So the electrons, all of our valence electrons of our metals are not held tightly to a specific metal. They are just held throughout. So this gives us a very kind of squishy solid. In that we can bend and manipulate it because of everything being kind of loosely bound. So this electron C model is the reason why metallic solids are malleable and ductile. So if we think about a metal, we can generally bend them pretty easily, unless they're just like really, really hard. But like a lot of times they're pretty easy to bend. They're not brittle, and it's because those positive metal ions can kind of push past each other and aren't rigidly placed. So they're malleable. Malleable is the ability to kind of beat a metal into a shape. Ductile, the ability to pull it into a wire, and conductive, the ability to move heat or electricity through that material. So those are all based on the electron C model, or the reason that the for those properties because of that electron C model. Some other things about metallic solids, they are going to have variable melting points. So we have mercury, which is a liquid at room temperature. So its melting point is below room temperature. And then we have tungsten, which is a melting point in the 3000s on the centigrade scale. So we have a really large range of melting points for our metallic solids. Our next type of solid is going to be a molecular solid. Or actually, let's go with ionic solid next. An ionic solid is a solid made of cations and anions. Actually, I'm going to put this on the next slide. So these are going to be, when we look at ionic solids. These are going to be ions beyond count. So this is an example of an ionic solid, specifically sodium chloride or salt. So it has ions beyond count. And just like our metallic solid, and I should have specifically said this is an extended solid. An extended solid is one that will just keep going on and on until you cut off the crystal or end the crystal. Same thing goes on with our ionic solid. This is also a extended solid. So the bonds that are bonds between our cations and anions stop when you cut off the crystal. So this is held together by ionic bonds. And ionic bonds are really strong, and the entire structure is held together by ionic bonds. And because of that, this is going to be something that has really high melting point. However, unlike our metallic solid, where our atoms themselves are able to move past one another, here we've got a solid where we have cations surrounded by anions, anions surrounded by cations, and if we shift any of those ions at all, we end up with repulsion. So this is a very rigid structure. So it does not have the ability to bend like a metal will. A great example of this would be you're able to really easily grind salt, right? So you can take salt and you can grind it up really, you know, with just a little mechanical force. It doesn't bend, it's brittle and breaks apart. And it's because of the structure itself. If you add any shearing force, it will completely shatter the crystal. Also, because all of the ions are set in a specific place, you do not have the ability to move charge. So this is going to be insulating as a solid. So you can't really move anything. Everything's kind of rigidly placed, so you can't move ions or you can't move charge. To have something that's conductive, it has to have the ability to move charge. However, if you were to melt an ionic solid, you would add enough energy in there to be able to have freely moving ions. So you can, this is conductive as a, in the liquid state, or what we call molten state, or as an aqueous species. What is conductive? Conductive as a liquid, or an aqueous species. Okay. Our next type of solid is a molecular solid. This is where we have molecules as our solid points. And they're held together by intermolecular forces. This is the only one that's held together by intermolecular forces. So this is not held together by bonds. This is held together just by an electrostatic force. So this is going to be the lowest melting of all of them, and it is not an extended solid. This is what's, so say discrete. These are discrete molecules. This is not an extended solid. And this is going to, because all that's holding it together is intermolecular forces, this can have low melting points. But there are no charges whatsoever, so this is also insulating. And our last type of solid is a covalent network solid. So this is similar to a molecular solid. Real quick as a note, just to kind of remind, molecules, these are non-metals bonded together. I should have said that. But they're molecules, like water would be an example, if it's in the solid state. We have like methane if it was in the solid state. So any of these where we have a discrete molecule in the solid state would be a molecular solid. Oh, I2 would also be a molecular solid. And that one's actually a solid at room temperature. Okay. And then covalent network solids, this is an extended solid with covalent bonds. So the whole thing has covalent bonds holding it together, but it is an extended solid, unlike a molecular solid where everything's held together by intermolecular forces. So covalent network solids themselves, they are a bunch of different, they are atoms beyond count. So this just keeps going on and on. So the solid itself goes until, again, you cut the solid itself, or the bonds, the covalent bonds go on and on and on until you cut the solid off. So that's why it's considered an extended solid. And because we have covalent bonds and atoms beyond count, this is going to be another really strong solid. This is going to be high melting. It's going to be brittle. And it's going to be what's called semiconducting. So most of the components in a computer that aren't plastic are composed of semiconductors, which are covalent network solids. These they have the ability to conduct electricity to a degree, but not to the degree that a metal can. Some examples of this. Most of them were pretty easy examples. This one, probably a little bit harder. Silicon solid would be an example. So like the things that silicon wafers are made out of for semiconductors or for solar cells. Silicon dioxide, which is glass or sand. Um, Germanium solid would be another example. Carbon solid, specifically diamond, carbon nanotubes, those type of things. And those are our different types of solids. I will have to finish module 2. I'll probably do another one of these tomorrow. So we can finish off module 2. I did not mean to talk as much as I did. I was going to do this shorter. Sorry about that. I'll get a little bit more brief next time. But does anyone have any questions about this content specifically before we end?
Hi, I was just wondering if you could go back to the ionic solid page.
Yeah, sure. Okay.
Thank you.
Yeah, of course. Okay. All right. I'm sorry that I have to go. I usually will be able to spend this entire hour, although I do hope to make this less than an hour so it doesn't take as long. But yeah, thank you guys. I will put, so it'll probably be at about 6 again tomorrow, and then we'll do 6 every week, as long as that works with everybody. All right. Thank you guys. Have a great day.
Thank you, you too.
Thank you.